Welcome back. In this video, we're going to talk about the form of a logical operator. So far in this playlist, we've seen the following logical operators. We saw the logical not operator, which was a unary operator. In other words, it accepted only one input that showed up to the right of the small tilde. The equivalent function notation for this operator was called the not function. We went down to our first binary logical operation, which was called the AND operator, or the logical AND operator, that was denoted using the ampersand in MATLAB. This was a binary operator because on the left and right side of that ampersand, we actually placed logical variables. The equivalent logical function was the AND function, lowercase a n d. Finally, the last binary operator that we've seen so far uses the vertical bar or the pipe symbol. That's the shift / key on the keyboard. That is also a binary operator since on the left and right side of that vertical bar, we actually place logical variables. The equivalent function in MATLAB was the OR function. One interesting feature of the form of logical operators is that each of these logical operators depends on predetermined values in order to get an exact truth value or to evaluate the operator. What I mean by this is let's go into the command window and let's clear all the variables and then clear the command window. If I type P and Q, MATLAB cannot evaluate the truth value for this general form because proposition P, or variable P, is not defined in memory. So too, proposition Q has no value in memory. Specifically, if I type Q, notice it's not a recognized variable. This form of a proposition, this form of an operator says, whatever the value of P is and whatever the value of Q is, take the AND operator between them and produce the corresponding truth value for the P and Q. However, in order to transform the form of a proposition or the form of a logical operation into an actual truth value, we need to pre-assign values of P and Q to get the actual truth value out. So for example, if I type P is true and Q is false, all of a sudden, when I type P and Q, now that proposition has an actual truth value. The general form of the proposition is an AND, but the truth value depends on the pre-assigned values for P and Q. In other words, we can talk about the abstract concept of the form of a proposition and then realize an individual truth value by assigning individual values in the variable. Another way to say this is that when we look at the truth tables, these things run through all possible values of the input and then show what the output should be under the appropriate conditions. So the form of this operation is not P. The actual truth value of the output not P depends on the assigned value for the proposition P. So when P is true, equal to 1, not P is false. When P is 0, not P is 1. Similarly, when we look at P and Q, the form of that proposition tells us general structure or logical rules. However, in order to actually realize a truth value, we need to assign truth values to the appropriate components of that logical operation. So when the P component is true and the Q component is true, the corresponding P and Q statement then becomes true also, because the AND operation isn't true exactly when both inputs are also true. In other words, when we're looking at the form of an operation, there are a few different features to be aware of. Number one, how many different inputs does that operation have? Number two, where are those inputs located? Number three, what is the truth value assigned to the operation with respect to the truth values of the components or the inputs to that operation? Let's go step by step. We'll start with the NOT operator in MATLAB. When we use the NOT operator, that was a unary operator. Specifically, we used the little tilde, and then on the right of that tilde, we placed a logical variable. That could be a logical scalar, a logical vector, or a logical matrix. When we put NOT P, whatever that variable is, every individual logical scalar in that array turned to its opposite. So all 0 entries turn to 1 and all 1 entries turn to 0. In other words, whatever the size of the input, the output had the same size, and specifically the individual scalars flipped to their complement. When we actually called this notation, notice we had operator notation with the symbol tilde used as the not operator. We also had function notation. The function for this one was called not. And then the inside of the parentheses, that's where we input the single proposition or the single logical array. The output was similarly the same size as the input. So here on the top, we had what we call operator notation. The not operator had a single input. This was a unary operator. And that meant that the not function was also one input. The output associated with each of these, we're calling this O1 for one output, took the same dimensions as the input, it just flopped the symbols. When we move down to the AND operator, notice this is a binary operation because on the left and right side we had logical variables as the input. Right now we focused on those logical variables have identical dimensions, so it could be both logical scalars, both logical vectors of the same sizes, or both logical matrices having the exact same dimensions. We had two different ways to call that, one of which was with the ampersand logical AND operator. On the left-hand side and the right-hand side, we had logical matrices. The output of that call was a logical matrix with the same size as the two inputs, at least up until this point. This operator notation took advantage of the binary ampersand. We could have also used the AND function. The AND function, the left operand of this operator goes in the first argument of our function, and the right operand goes into the second argument. The output, again, O1 means first output, is a matrix of the same size. So the left component, right component, goes to the left and right of the ampersand or to the left and right of the comma using function notation. The last operator that we talked about with logicals was the OR operation where we're using the pipe symbol or the vertical bar. To the left and the right, we have a logical matrix of the same size at this point. Then we output a matrix with the exact same dimensions. The truth value of each logical scalar entry of that output is literally the truth value of the corresponding logical scalars of these particular variable inputs. We could use operator notation or we could use function notation. The left operand for this thing becomes the first input, and the right operand for the vertical bar becomes the second input. The output is identical using either of these function calls. The point of this video is to make very, very clear, if I have nothing in memory and I try to call P or Q, that call gives this general form of a logical operator, but it will have no truth value unless I specifically assign truth values for the variable P and truth values for the variable Q, at which case that point we can actually find what is the truth value of the statement P or Q. This is useful in computer programming because when we're setting up a program, we don't know a priori what the truth value of the input is, but we may know what form we want to make decisions. The last thing we're going to end on is a discussion of syntax of MATLAB functions. This goes back to a previous video where we talked about using built-in functions. We're going to add some nuance to that syntax. Every time we call a predefined function in MATLAB, the first letter of that function is a lowercase. The function itself is defined by a predefined name. Then we do a left parentheses and right parentheses. And then we're going to put a number of inputs. In this case, I1 stands for input 1. I2 stands for input 2, and perhaps we say that we have n inputs. Some of these might be actual arrays, and some of them might be known as parameters, but the fact of the matter is we can put up to n inputs in general. After the function is called, MATLAB does some processing of this input data and then returns output data. In this case, these might be arrays, they might be strings, they might be characters. There could be a number of different types of output. We're going to call these m different pieces of output data. So O1 means output data 1, O2 means output 2, all the way to OM, which means output M. In the case of logical functions, notice that the not function is a one input, one output function. the input is assumed to be a logical matrix, and the output is a logical matrix using the exact same sizes. For the AND function, we have two inputs to that function, I1 and I2. In this video, we're claiming those inputs should be logical arrays with identical dimensions. The corresponding output, there is only one of them, is also a logical array with identical outputs. Similarly, when we look at the OR function, we have two inputs, each of which are logical arrays. They could be logical scalars, logical vectors, or logical matrices. The output is a logical array with identical dimensions as those inputs. When we think about the number of inputs used for a particular operator, in other words, when we use a symbol to do math in MATLAB, do we write inputs on the left and right? Do we write it only on the left or only on the right? The function realization has a similar structure. It's just instead of using a symbol, we use a function name. With that, we end this video. I welcome your comments and questions below, and I'll see you in the next video.